1881. Pittsburgh, Pennsylvania. The smoke from Carnegie's Homestead works carried the scent of molten iron and American ambition through air, thick with industrial revolution. European steel experts had arrived to witness what they called the American experiment, a single integrated plant attempting to produce 300,000 tons of steel annually while maintaining quality standards. Through the thunder of blast furnaces and the rhythmic hammering of steam-powered machinery, something unprecedented was taking shape. American engineers were melting iron ore, mixing metals, and rolling finished steel without ever letting the material cool, a continuous flow process that European batch production methods said was impossible to control at massive scale. In European mills, master craftsmen produced 50 tons per day using centuries-old techniques, small-scale operations, traditional blast furnaces, time-tested methods that had dominated global steel markets since the industrial age began. But Andrew Carnegie's Homestead Works was operating on principles European steelmakers had never imagined necessary. Vertical integration from iron mines to finished products, automated systems replacing skilled labor, production volumes that dwarfed entire European operations. The contradiction seemed impossible. How could American industrial methods, dismissed as crude and unsustainable, outlast European tradition by over a century while modern efficient mini-mills collapse in just 15 years? The year 1881 marked the pinnacle of European steel dominance, with British mills controlling global trade through methods perfected over generations of industrial refinement. From the coal-blackened valleys of Sheffield to the mechanized workshops of the Ruhr, European steelmakers operated with the confidence of proven tradition, small-scale production facilities, where skilled craftsmen guided iron through time-tested blast furnaces that rarely exceeded 50 tons of output per day. These operations had built the railways that connected London to Edinburgh, forged the ships that carried British goods across oceans, and created the structural foundations upon which European cities expanded skyward. American industrialists of the early 1880s understood their position as apprentices to European mastery. They imported not just European expertise and European designs, but European assumptions about what steel production should fundamentally represent. The prevailing wisdom held that quality steelmaking required intimate human control at every stage. Master puddlers who could read the color of molten iron like ancient auguries, skilled rollers who shaped red-hot metal through intuitive understanding passed down through apprenticeship systems that stretched back decades. Scale, according to European doctrine, was the enemy of precision. But America faced a challenge that European geography and modest demand had never forced upon their steelmakers. The transcontinental railroad, that ambitious steel ribbon stretching across a continent, required 150,000 miles of steel rail, more than the combined railway networks of Britain, France, and Germany. Growing American cities demanded structural steel for bridges spanning the Mississippi, the Ohio, and the Missouri, great rivers whose continental scale dwarfed the Thames or the Rhine. The Brooklyn Bridge alone required 14,000 tons of steel wire, more than many European mills produced in entire years. European methods, perfected for island geography and established markets, proved economically catastrophic when applied to American scale. The mathematics were brutal and unforgiving. Small batch production meant constant stopping and starting, with furnaces cooling between heats and requiring expensive reheating cycles that consumed enormous quantities of coal. Traditional blast furnaces operating at 50 tons per day would need 300 separate facilities to meet the steel demands of a single major American railroad expansion, an impossible concentration of capital and skilled labor that no American company could sustain without bankruptcy. Transportation costs compounded the crisis. European mills operated within compact industrial regions where iron ore, coal, and limestone lay within horse cart distances of production facilities. American raw materials scattered across a continent, iron ore in Minnesota's remote Mesabi Range, coking coal in Pennsylvania's mountains, limestone quarries hundreds of miles from either. Moving these materials to separate small-scale facilities and then shipping finished products to distant markets created cost structures that made American steel uncompetitive against imports from European mills that enjoyed geographic advantages American producers could never replicate. The skilled labor shortage presented an even more devastating obstacle. European craftsmen commanded wages reflecting their specialized expertise, wages calculated for European productivity levels and European market conditions. But American scale demanded worker productivity that European training systems had never contemplated. A skilled puddler who could manage 2 tons of molten iron per shift using European methods would need to oversee 20 tons per shift to make American operations economically viable. European trained workers, accustomed to traditional batch rhythms and small-scale quality control, found themselves overwhelmed by American production demands that required continuous operation at speeds their apprenticeships had never prepared them to sustain. By 1882, the crisis had reached desperate proportions. American steel companies faced a stark choice that would determine the industrial future of the nation. They could abandon domestic production and resign themselves to permanent dependence on European imports, accepting that American industry would remain forever subordinate to European technological superiority. Or they could attempt something unprecedented in the history of metallurgy, engineering an entirely new approach to steelmaking that integrated every aspect of production on a scale that no civilization had ever achieved. Andrew Carnegie recognized the magnitude of this challenge when he announced his intention to purchase the troubled Homestead Works in 1883. Critics within the American steel industry dismissed his plan as industrial suicide. The Iron Age magazine, the most respected publication in American metallurgy, declared integrated steelmaking a costly American experiment that would inevitably collapse under the weight of its own complexity. European steelmakers, observing Carnegie's proposals from across the Atlantic, pronounced his vision industrially unsound. No single facility could efficiently produce 300,000 tons annually while maintaining the quality standards that steel buyers demanded for critical applications like railroad construction and bridge engineering. The existing Homestead Works exemplified everything wrong with American attempts to replicate European success. The facility's Bessemer converters, designed according to British specifications, couldn't handle the chemical composition of iron produced from Pennsylvania mines. The plant layout followed European small-scale logic, with separate buildings for each production stage connected by expensive transportation systems that wasted heat and labor. Most critically, the operation employed European production rhythms that created constant bottlenecks, periods of frantic activity followed by idle waiting as different departments fell out of synchronization. Carnegie understood that purchasing Homestead meant accepting complete responsibility for proving that American industrial methods could succeed where European tradition had reached its limits. The stakes extended far beyond the survival of a single steel company. If Carnegie's integrated approach failed, American industry would remain permanently dependent on European imports, and the nation's industrial development would be constrained by the production capacity and pricing decisions of foreign competitors who controlled global steel markets. The transformation would require more than capital investment or technological innovation. It would demand a fundamental reconceptualization of what steel production could become when freed from European assumptions about scale, integration, and continuous operation. Carnegie was proposing to engineer an industrial ecosystem that could sustain itself through economic downturns, adapt to changing market demands, and operate profitably at production volumes that European steelmakers considered theoretically impossible to achieve while maintaining quality standards. Carnegie's secret weapon arrived at Homestead in 1884 not as imported European expertise, but as Captain William Bill Jones, a self-taught American engineer whose understanding of molten metal flow would revolutionize steelmaking forever. Jones possessed an intuitive grasp of heat transfer and continuous processes that surpassed formally trained European metallurgists, constantly sketching improvements on scraps of paper and testing configurations that violated every principle of traditional batch production. While European steelmakers viewed their craft through the lens of centuries-old apprenticeship systems, Jones approached steel production as a fluid engineering problem that demanded American solutions for American scale. The fundamental flaw in European steelmaking became crystal clear to Jones during his first weeks at Homestead. European methods were built around batch production, a stop-and-start approach where iron was melted, allowed to cool, then reheated for the next production stage. This cooling and reheating cycle wasted enormous quantities of fuel and time, creating bottlenecks that made large-scale continuous operation economically impossible. Jones recognized that American steel production would never achieve competitive costs while following European rhythms designed for small-scale craftsmanship rather than industrial efficiency. Jones's breakthrough invention emerged from this realization: the Jones mixer, a revolutionary 150-ton vessel that resembled a massive tea kettle lying on its side. This cylindrical furnace could receive molten pig iron directly from multiple blast furnaces, blend different grades of iron for consistent chemical composition, and maintain the metal in liquid state for hours while feeding it continuously to steel converters. The mixer eliminated the costly cooling and reheating cycles that crippled European operations, creating a continuous flow of molten metal that European batch methods could never achieve. The engineering specifications of the Jones mixer revealed the magnitude of its innovation. Traditional European blast furnaces produced pig iron that cooled in sand molds, creating individual ingots that required remelting before steel conversion, a process that consumed 2.5 tons of coal per ton of finished steel. The Jones mixer received molten pig iron at temperatures exceeding 2,000 degrees Fahrenheit, maintained that heat through carefully controlled combustion, and delivered liquid iron to converters without energy-intensive reheating. This continuous process reduced coal consumption to 1 8/10 tons per ton of steel, a 28% reduction that saved $50,000 monthly in fuel costs alone, equivalent to approximately $1.7 million in modern purchasing power. But Jones's vision extended beyond fuel efficiency to encompass the entire production flow. While Europeans built steelmaking facilities as collections of separate buildings, each housing individual production stages, Jones designed Homestead as an integrated system where molten metal never cooled from blast furnace to finished product. He positioned blast furnaces, mixers, converters, and rolling mills in carefully calculated proximity, connected by overhead cranes capable of moving 300-ton ladles of molten steel with clockwork precision. The central building housing the open hearth operation stretched 967 feet in length, creating an uninterrupted production line that European facilities, constrained by traditional small-scale thinking, had never attempted to construct. The breakthrough moment that validated Jones's revolutionary approach came on a cold morning in 1886, when Homestead's first open hearth furnace, the largest in America at that time, produced its inaugural heat. 75 tons of perfect steel emerged in 8 hours compared to European open hearth methods that required 24 hours to produce 40 tons of equivalent quality. The numbers represented more than incremental improvement. They demonstrated that American continuous flow principles could achieve productivity levels that European batch production considered theoretically impossible. Jones's success attracted skeptical European observers who arrived at Homestead expecting to witness the collapse of American industrial experimentation. Instead, they encountered production methods that challenged fundamental assumptions about steelmaking that had remained unchanged since the early days of the Industrial Revolution. European visitors watched in amazement as Homestead's integrated systems processed raw materials into finished products without the cooling delays that characterized traditional methods, achieving quality standards that equaled or exceeded European craftsmanship while operating at scales no European facility had ever attempted. The continuous flow system created advantages that compounded throughout every aspect of production. European steelmakers lost enormous amounts of heat energy during cooling and reheating cycles, but Jones's integrated approach captured and utilized thermal energy that European methods wasted. The mixer's ability to blend iron from multiple blast furnaces ensured consistent chemical composition that European batch methods, dependent on individual furnace variations, struggled to achieve. Most importantly, the continuous operation eliminated the idle time that plagued European facilities, where workers and equipment sat unused during cooling and reheating periods. Jones's engineering revolution extended to the workforce itself. European steelmaking required master craftsmen whose skills developed over decades of apprenticeship, creating labor bottlenecks that limited production capacity. The continuous flow system allowed Jones to train American workers in specialized functions within the integrated process, developing expertise focused on maintaining steady production rather than managing the irregular rhythms of batch operations. Workers became experts in continuous operation rather than intermittent craftsmanship, creating a labor force adapted to American industrial scale rather than European small batch traditions. By 1887, the results spoke with mathematical certainty. Homestead's continuous production systems were achieving output rates that European steelmakers had declared impossible, while maintaining quality standards that equaled traditional methods. The facility processed raw materials into finished steel products with fuel efficiency and labor productivity that surpassed European operations by margins so significant that visiting European engineers initially questioned the accuracy of Carnegie's production records. Jones had proven that American industrial methods, dismissed as crude experimentation by European experts, could achieve superior results through systematic engineering rather than traditional craftsmanship. The Jones mixer became the technological foundation upon which Carnegie would build an integrated steelmaking empire that would outlast every European competitor. But Jones understood that revolutionary technology required equally revolutionary operational philosophy, a recognition that would drive Carnegie's next phase of development as the company prepared to implement what Carnegie called hard driving, the relentless technological upgrading that would transform American steel production from experimental innovation into industrial dominance that would reshape global manufacturing forever. Carnegie's philosophy of hard driving emerged in 1887 as a relentless commitment to technological upgrading that would have seemed wasteful to European steelmakers accustomed to operating equipment until complete failure. Carnegie demanded immediate replacement of any machinery that fell below peak efficiency, even if the existing equipment was nearly new and still profitable. If a blast furnace operated at 90% efficiency, Carnegie installed one that achieved 95% efficiency, discarding the original investment without hesitation. This approach violated every principle of European industrial conservatism, where facilities operated equipment for decades to maximize return on capital investment. The scale of Carnegie's technological revolution became evident through systematic automation that eliminated hundreds of manual positions while increasing production capacity. Traditional European blast furnaces required teams of workers to manually charge raw materials, iron ore, coke, and limestone into the furnace mouth using wheelbarrows and primitive elevators. Carnegie installed automatic charging machines that lifted measured quantities of materials to furnace tops using steam-powered mechanisms, eliminating 200 manual laborers per furnace while ensuring precise chemical ratios that manual charging could never achieve consistently. The crown jewel of Carnegie's mechanical innovation was the 48-inch universal plate mill, the largest rolling mill in the world when installed in 1889. This massive machine could roll steel plates 8 feet wide and up to 60 feet long, creating structural elements for shipbuilding and bridge construction that European mills, limited by smaller equipment, could not manufacture. The universal plate mill required steam engines generating 4,000 horsepower to operate its enormous rollers, consuming more energy than entire European steel plants, while producing steel plates that no combination of European facilities could duplicate. Carnegie's cost accounting system revolutionized industrial management through systematic measurement that European steelmakers had never implemented. Every pound of raw materials was weighed at every production stage, creating detailed records that tracked iron ore from Minnesota mines through blast furnace charging, pig iron production, steel conversion, and final rolling into finished products. This data revealed inefficiencies that European operations relying on traditional estimation methods never identified or corrected. Carnegie discovered that seemingly minor improvements, adjusting furnace temperatures by 50 degrees, modifying charging sequences, or changing rolling speeds could reduce costs by thousands of dollars monthly. The vertical integration strategy solved raw material supply problems through systematic control of every input from extraction to delivery. Instead of purchasing coal from independent suppliers whose prices fluctuated with market conditions, Carnegie acquired entire coal fields in Pennsylvania and West Virginia, ensuring steady supply at predictable costs. The iron ore purchases went beyond simple buying agreements to outright ownership of mining operations in Minnesota's Mesabi Range, the richest iron deposits in North America. Carnegie's mining engineers extracted ore using steam shovels and mechanical loading systems that reduced extraction costs below market prices while guaranteeing chemical consistency that purchasing from multiple suppliers could never achieve. Transportation integration completed Carnegie's control over production costs through railroad construction that eliminated dependence on independent shipping companies. The Carnegie railroads connected iron mines in Minnesota to coal fields in Pennsylvania and transported finished steel products to major markets in Chicago, New York, and Philadelphia. These railroads operated as profit centers that generated revenue from other customers while ensuring that Carnegie's raw materials and finished products moved at controlled costs regardless of fluctuations in commercial shipping rates. By 1890, the mathematical results of Carnegie's integrated approach demonstrated superiority over European methods through production numbers that seemed impossible to traditional steelmakers. Homestead employed 3,800 workers producing 400,000 tons annually, 8 times the output of comparable European plants, operating with similar workforce levels. The productivity advantage came not from longer working hours or reduced wages, but from systematic integration that eliminated the inefficiencies built into European small-scale operations. Production costs reflected the cumulative impact of Carnegie's innovations through dramatic reductions that made American steel competitive in global markets for the first time. Steel rails that cost $28 per ton to produce in 1880 fell to $11.50 per ton by 1892, a cost reduction of nearly 60% achieved while maintaining quality standards that equaled or exceeded European products. These cost advantages allowed Carnegie to capture American railroad contracts that had previously gone to British suppliers, establishing domestic steel production as economically superior to imports for the first time in American industrial history. The success bred its own challenges, as efficiency gains came with human consequences that European craftsman-based systems had never confronted. Carnegie's continuous improvement systematically eliminated skilled positions that had sustained steel workers for generations, replacing human expertise with mechanical precision that operated more reliably and cost-effectively than traditional methods. The powerful Amalgamated Association of Iron and Steel Workers recognized that mechanization threatened not just individual jobs, but their entire system of craft control that had regulated steel production since the industry's earliest days. The confrontation erupted in 1892 when Henry Clay Frick, Carnegie's partner responsible for daily operations, demanded wage cuts despite record profits generated by the efficiency improvements. The union's resistance reflected deeper concerns than immediate compensation. They understood that accepting reduced wages while productivity increased through mechanization would eliminate their leverage in future negotiations. If machines could replace skilled workers, then skilled workers lost the bargaining power that had protected wages and working conditions in European-style craft production. 3,800 workers struck Homestead in July 1892, shutting down production at the peak of the facility's efficiency. Frick's response demonstrated the ruthless logic of integrated production. He hired 300 Pinkerton guards to break the strike through force rather than negotiation. The confrontation turned violent as workers fought to maintain control over their workplace, resulting in 10 deaths and the complete destruction of Union influence at Homestead. The strike's outcome proved a brutal point about integrated mechanized production that European craft systems had never confronted. Carnegie's automated systems continued operating, with reduced workforce during the strike, demonstrating that advanced machinery could maintain production levels that traditional European methods required large numbers of skilled workers to achieve. The victory came at enormous reputational costs that damaged Carnegie's public image, but the technological foundation remained unshakable, positioning Carnegie Steel for the expansion that would make it America's dominant industrial enterprise. The violence at Homestead on July 6, 1892, began before dawn when 300 Pinkerton guards attempted to land at the steel works aboard 2 barges floating down the Monongahela River. Workers had barricaded the plant entrances and positioned themselves along the riverbank, determined to prevent Frick's private army from breaking their strike through force. The battle that followed lasted 14 hours, with workers using rifles, dynamite, and burning oil to repel the Pinkertons while the guards returned fire from their floating fortress. By evening, 10 men lay dead and 60 others wounded, but the technological implications of the conflict extended far beyond the immediate casualties. During the strike's 4-month duration, Carnegie's automated systems continued producing steel with a skeleton crew that would have been impossible under European craft production methods. The continuous flow processes that Jones had engineered operated largely independent of skilled labor once properly configured, allowing Homestead to maintain partial production even while union workers picketed outside the gates. European steelmaking, dependent on master craftsmen whose expertise could not be easily replaced, would have ceased completely during such a work stoppage. Carnegie's mechanized approach had fundamentally altered the relationship between labor and production, creating systems that could function despite workforce disruption. The strike's resolution came through Pennsylvania state militia intervention rather than negotiated settlement, establishing a precedent that would shape American industrial relations for decades. 8,000 state troops occupied Homestead in July, protecting replacement workers who operated Carnegie's machinery without union oversight. The defeated Amalgamated Association of Iron and Steel Workers lost not just immediate bargaining power, but their ability to control production methods through craft traditions that had regulated steelmaking since the industry's origins. Carnegie's victory demonstrated that integrated mechanization could eliminate union influence more effectively than negotiation or compromise. But the human cost of technological progress became apparent through systematic changes that transformed the nature of industrial work itself. Carnegie's efficiency improvements had eliminated positions that provided pathways from unskilled labor to master craftsman status, creating a workforce increasingly divided between a small number of highly trained technicians who operated complex machinery and large numbers of workers who performed repetitive tasks requiring minimal skill development. The apprenticeship systems that had allowed ambitious workers to advance through accumulated expertise became obsolete when machines replaced human judgment in most production processes. Frick's management philosophy treated labor costs as engineering problems requiring systematic solutions rather than human relationships demanding negotiation. He implemented time and motion studies that measured worker productivity with stopwatch precision, identifying inefficiencies that could be eliminated through better organization or mechanical assistance. Workers who had once controlled their own pace and methods found themselves operating according to schedules determined by machine capacity rather than human rhythm, fundamentally altering the experience of industrial labor from craft work to factory discipline. The reputational damage from the strike followed Carnegie for the remainder of his career, transforming public perception of him from innovative industrialist to ruthless capitalist who valued efficiency above human welfare. Newspaper coverage of the Homestead violence portrayed Carnegie as abandoning American workers in favor of mechanized production that eliminated jobs while increasing profits. The contrast between Carnegie's public philanthropy and private labor policies created lasting criticism that his charitable giving represented guilt over industrial methods that enriched owners while impoverishing workers. Yet the technological innovations continued accelerating even during the strike's aftermath, as Carnegie recognized that superior engineering rather than lower wages would determine long-term competitive advantage. Between 1893 and 1898, Carnegie completely rebuilt most Homestead facilities, installing furnaces so advanced they reduced labor costs by 50%, while setting production records that amazed industrial observers worldwide. The new open hearth furnaces operated at temperatures and throughput rates that surpassed any European facilities, demonstrating that American engineering leadership had moved beyond copying foreign methods to establishing global technological standards. The economic logic of Carnegie's approach became undeniable through cost reductions that made American steel competitive in international markets previously dominated by European suppliers. Steel production costs at Homestead fell below $8 per ton by 1895, compared to European costs that remained above $15 per ton due to higher labor expenses and smaller-scale operations. These cost advantages allowed Carnegie to export American steel to European markets for the first time, reversing the trade relationships that had made America dependent on foreign industrial products throughout the earlier 19th century. Carnegie's Systematic integration of raw material control, transportation, and manufacturing created an industrial ecosystem that operated more efficiently as scale increased, the opposite of European small-scale production where unit costs rose with expanded output. Larger blast furnaces achieved better fuel efficiency than smaller ones. Longer production runs reduced setup costs per ton of finished steel. Higher capacity rolling mills spread equipment costs over greater output volumes. Every aspect of the integrated system became more economical as production increased, creating sustainable competitive advantages that European craft methods could not match. The strike's ultimate significance lay not in its immediate violence, but in proving that mechanized production could operate independently of traditional labor relationships that had defined industrial work since the Industrial Revolution began. European steelmakers continued relying on skilled craftsmen whose cooperation was essential for production, giving workers substantial bargaining power that limited management flexibility. Carnegie's automated systems reduced dependence on irreplaceable human skills, shifting power decisively toward owners who controlled capital equipment rather than workers who possessed specialized knowledge. By 1895, Homestead operated with unprecedented efficiency that vindicated Carnegie's integrated approach through production statistics that European competitors could not duplicate. The facility produced over 600,000 tons annually with a workforce of 4,200 workers, productivity levels that exceeded European plants by more than 300% per worker. Quality standards remained consistently high due to mechanized precision that eliminated the variations inherent in handcraft production, creating steel products that met specifications with reliability that European methods could not match. The human price of this technological revolution created lasting tensions between industrial efficiency and worker welfare that would influence American labor relations well into the 20th century. But the engineering foundations established at Homestead proved economically superior to all alternatives, creating an industrial model that would define American manufacturing leadership for generations, while European competitors struggled to adapt their traditional methods to the demands of modern large-scale production. The Panic of 1893 provided the ultimate test of Carnegie's integrated model against economic catastrophe that destroyed smaller steel companies across America. When financial markets collapsed in May 1893, steel prices plummeted from $28 per ton to $12 per ton within 6 months, forcing dozens of independent producers into bankruptcy. Carnegie's response revealed the strategic advantages of vertical integration instead of reducing production like competitors. He implemented his crisis strategy of cutting costs while running mills at maximum capacity to capture market share from failing rivals. The integrated model's resilience became apparent as economic conditions that devastated competitors actually strengthened Carnegie's competitive position. When steel demand collapsed, suppliers to independent steel companies raised prices to compensate for reduced volume, squeezing profit margins that were already thin due to falling product prices. Carnegie's ownership of iron mines, coal fields, and transportation systems insulated him from supplier price increases, maintaining input costs at predetermined levels while competitors faced escalating expenses that made continued operation impossible at reduced steel prices. Carnegie's massive scale provided decisive advantages when demand fell below normal levels. Independent steel producers operating single blast furnaces or small rolling mills faced fixed costs that became prohibitive when production volumes declined. Carnegie's integrated facilities could maintain profitable operation at 60% capacity, while competitors required 80% capacity to avoid losses. This operational flexibility allowed Carnegie to continue production while rivals shut down completely, positioning Homestead to supply customers who could no longer rely on smaller producers. The crisis strategy of meeting any price while maintaining full production proved economically devastating to competitors who lacked Carnegie's cost structure. When railroad companies solicited bids for steel rails at $12 per ton, independent producers calculated losses of $3 to $4 per ton at those prices. Carnegie's integrated costs allowed profitable production at $11 per ton, enabling him to underbid every competitor while maintaining margins sufficient to fund continued expansion. Competitors who attempted to match Carnegie's prices faced bankruptcy within months. Diversified product lines provided additional stability that specialized producers could not achieve during economic downturns. When railroad construction declined during the Depression, Carnegie's structural steel business supplied building construction in major cities that continued despite reduced economic activity. When bridge construction slowed, Carnegie's armor plate division received naval contracts from the United States government that provided steady revenue streams independent of commercial steel demand. This diversification allowed Homestead to maintain production levels while competitors dependent on single product categories faced complete demand collapse. By 1898, economic recovery revealed the permanent changes that the Depression had created in American steel production. 26 independent steel companies had failed during the crisis, leaving Carnegie with dominant market share that would have taken decades to achieve under normal competitive conditions. The survivors were primarily companies that had adopted elements of Carnegie's integrated approach, demonstrating that traditional European-style small-scale production could not withstand major economic disruptions in American market conditions. When J.P. Morgan orchestrated the purchase of Carnegie Steel for $480 million in 1901 to form United States Steel Corporation, the transaction represented recognition that Carnegie's integrated model had become the standard for successful American steel production. The Homestead Works became the flagship facility of the world's first billion-dollar corporation, validating Carnegie's belief that American industrial methods could achieve scale and efficiency that European competitors could never match through traditional approaches. The plant's integration, scale, and continuous innovation sustained production through challenges that would have destroyed smaller operations throughout the following decades. During World War I, Homestead produced armor plate for American warships while simultaneously manufacturing structural steel for shipbuilding facilities that expanded American naval capacity. The facility's ability to shift production between military and civilian applications demonstrated operational flexibility that specialized plants could never achieve. The Great Depression of the 1930s tested Carnegie's integrated model against economic conditions even more severe than the Panic of 1893. While numerous smaller steel producers failed completely, Homestead continued operating at reduced capacity, maintaining workforce employment and production capability that enabled rapid expansion when economic conditions improved. The plant's diversified product lines and integrated cost structure provided the resilience necessary to survive economic downturns that eliminated competitors lacking similar operational advantages. World War II demonstrated the strategic importance of integrated steel production when Homestead operated at maximum capacity, producing materials essential for American military success. The facility's continuous operation capabilities enabled round-the-clock production of steel for ships, tanks, aircraft, and munitions that smaller, less integrated facilities could not have sustained. The plant employed 15,000 workers at its wartime peak, producing over 2 million tons annually, production levels that vindicated Carnegie's original vision of American industrial scale. The final accounting reveals the extraordinary durability that Carnegie's integrated approach achieved through systematic engineering rather than short-term optimization. Homestead operated for 105 years, from 1881 to 1986, producing over 100 million tons of steel while surviving economic depressions, 2 world wars, multiple recessions, and dramatic changes in steel markets that eliminated most competitors. The plant's longevity resulted from operational principles that prioritized adaptability and resilience over immediate efficiency. Modern mini-mills, designed according to different economic principles, demonstrate the contrast between optimization for current conditions versus engineering for long-term survival. These facilities require capital investments of only $140 to $200 per ton of capacity compared to $1,000 for integrated plants, offering apparent efficiency advantages that attract investors seeking rapid returns. Mini-mills achieve greater flexibility through specialized production focuses and simplified operations that can respond quickly to market changes. Yet, mini-mills typically operate for 10 to 20 years before closing, victims of commodity price cycles, electricity cost fluctuations, and scrap steel availability problems that integrated plants like Homestead weathered through diversification and scale advantages. When steel prices crashed during regular 7 to 10-year cycles, many mills lacked the operational flexibility and cost structure advantages that sustained Carnegie's integrated approach through multiple economic downturns. Modern steel production optimizes for efficiency and flexibility while sacrificing the resilience that enabled Homestead's century-long operation through systematic integration that created sustainable, competitive advantages no specialized facility could replicate.